Welcome everybody. We're going to talk about reactions of alkenes. We talked about regioselective reactions, specifically acid addition, non-stereospecific, Markovnikov, and anti-Markovnikov reactions. Let's talk about not regioselective but stereospecific reactions. What does non-regioselective mean? It means that when you have an alkene, let's say you have a trans alkene like this, something like this that I've drawn here. They will attack electron deficient electrophiles. It has an equal opportunity of going on either this end or this end. 50-50. There is no selectivity there. That's called non-regioselective. But in this case, we're going to talk about addition of a halogen, specifically bromine or chlorine, to the alkene. This has directional attack. So it doesn't attack in either direction. It is going to attack specifically in a certain direction. And we are going to see why that is. Let's take, for example, this alkene. The blue lobes that you see are just pi orbitals. I know they look a bit weird. I just put those dots just to show you, there are 2 electrons in here. But the electrons are all over the orbital, as you know, and they are above and below the sigma bond. So when you take these alkenes, they are electron rich. So they will only really attack electron deficient electrophiles. So these are nucleophiles. This is a very nice, soft nucleophile. Let's say a bromine comes in. Now, a bromine, you always seen bromine as Br minus, right? So, well, a Br minus is a nucleophile, and this is a nucleophile. There's not going to be any reaction between the two because they're both the same charge, and like charges repel. In this case, when you have bromine in CCl4, bromine, is electron negative. And momentarily, the bromines here have a tug-of-war for these electrons just to get an octet. Just in like a split, microsecond, these electrons can move over here. These are large polarizable atoms. And for a teeny bit of a second, you can get a Br plus. I know it sounds terrible that bromine can actually have a positive charge, but remember that it is also a very large atom, so it can spread that charge internally. Now this Br plus is your electrophile, not the Br minus. So the Br plus is your electrophile, and that pi bond is your nucleophile. Now we are in business. So let's say you have your pi bond like this, and your bromonium comes in. It's got only 6 electrons. It wants another extra pair of electrons. It's trying to grab this, and it's a huge atom. So it's like this huge mama atom, and it cannot squeeze it on this end or this end. It's going to go, I'm going to sit on this entire sofa here, and it sits right in the center. So it catches both the p orbitals. All right, so you will get an intermediate where you have a triangular 3-membered ring. And so you have a intermediate here with the bromonium, with the carbons. That's it, a 3-membered ring here. So this bromonium has a specific shape. Now, well, you don't want to be floating around as a positive for too long because you're in a very non-polar solvent. There's no stabilization here like in a water environment. So the second it forms, well, something's going to attack it to relieve it of this strain. It's got angle strain here. And what is the thing that has electrons here? The bromide. So now this is your electrophilic bromonium intermediate. And this is your nucleophile. Your nucleophile is going to try to shove those electrons in here. Well, it sees this. The sigma bond has an anti-bonding CBr sigma star bond. And it's going to go right into there and put its electrons in there and open that up. So now you have your bromines on opposite sides. And that is called an anti-addition. The stereochemistry of the original molecule, the trans stereochemistry, is preserved because all throughout we didn't have a carbocation or an opportunity to rotate that bond. So therefore your trans stereochemistry is preserved all the way to your product. So can this Br minus attack from the top? Why does it always have to attack from the bottom? Well, look at it. Here you have 3 pairs of electrons on this bromonium ion. You have 4 pairs of electrons on this bromide. They're going to be butting heads. There's too much repulsion on the top. So they have to come in from the bottom and attack anti to that bond. Let's draw that out. So we have here a Br plus, and I'm going to show the Br plus here being attacked. You could also draw arrows directly here and kick that out. So the pi bond reaches out and catches the Br over here, and as I said, it is going to catch it so that it sits right in the center. So now you have a carbon here, and now it's not going to be a flat carbon, so I'm going to draw dashes and wedges here from the intermediate because you are forming a carbon that has 4 bonds now. In the transition state, the pi bond is breaking and it is spread between the bromine like this, and the bromine has got a positive charge. So this is the transition state. The bonds haven't really gelled in yet, and then when they do, it's called an intermediate, and you will see that the stereochemistry, which is trans or E, is preserved throughout the entire molecule. And this is going to be a bromonium with a positive charge. And the intermediate here is going to have a positive charge. You can draw the positive here, or you can draw it outside. You could also very well put it right here in the middle as well. Now that you have this, then as I said, here's the big yellow balloon here, and the other balloon cannot come in from the top. The other Br minus is going to attack from below. Now there are 2 carbons here that can be attacked by this. Which one is it going to attack? Equal opportunity to attack either one of these. So therefore, let's label this A and B and see what happens when you attack either one. Let's say I attack A here. So I bring in my molecule here, and I'm going to redraw this here and attack it with A. All right, so your Br minus is going to attack this, and it can attack this at A or B. And let's draw both cases here. So if it attacks over here, it's going to pop this open and go in from the rear end. And so now you are going to have a carbon-carbon bond. And as I said, the stereochemistry is preserved, and you will have your bromines going in on opposite sides of this molecule. So here your methyl groups are going to be on opposite sides. Trans, one is on a wedge and one is on a dash. Your bromide makes a bond here at A carbon. Anti-addition. Now over here, you can see that this could happen again on this B carbon. And again, I'm just going to draw a Br minus attacking that, and the lone pairs go in and give electrons into this CBr anti-bonding orbital here, and it's going to pop that open and in the same direction as that orbital, and then it's going to pop that open, and you are going to get anti-addition on B. So here your methyl and your hydrogen are going to be on the opposite sides, just like they are on your starting material, because the stereochemistry is preserved throughout the entire reaction. And you will get your bromides adding anti. Why? Because the Br minus cannot attack from the top. It has to attack from the bottom. All right, so this is a good time for you to hit that pause button and tell me what is the relationship between A and B. Are they the same? Are they enantiomers? Are they diastereomers? Are they meso? What are they? Well, if you look at this, you may think, oh, I can put a mirror in here and I can get a perfect reflection here. Is that right? Do you think they're enantiomers? Well, before you conclude, let's try to see if they are going to be superimposable or not. If they are superimposable, then they are not enantiomers. Enantiomers are non-superimposable mirror images. Well, in order to do that, let's align the bromides with this to see if they're superimposable. So take this and flip it just 180 degrees. So they're just a rotation. So just take this molecule and just rotate it like this. I'm not doing any kind of reflection, just taking this molecule and rotating it. Let's do that, just so we can check to see if they're superimposable or not. Carbon-carbon bond is going to come over here, and the bromides are then going to be in opposite places. This is going to come over here, and this is going to come over here when you do a rotation. The methyl group that's sticking out here when you rotate is going to go behind. And the methyl group that's behind, when you rotate it, it's going to come in front. Well, what do you think this is going to look like more and more? And it's the same here. The hydrogens are also going to be 180 degrees rotated. So your hydrogen is going in here, and your hydrogen is coming out here. Well, what do you think? Are these superimposable? Are they superimposable? You can see how you can take this and put it right on top of it, and it's going to fit perfectly. So A and B are the same. They are not mirror images here, just because they're superimposable. But are they achiral or chiral? Well, let's check this out. You don't have a mirror plane of symmetry anywhere here in this molecule when it's drawn like this. But if you put both the bromines on the same side, you would be able to find a mirror plane of symmetry. So let's draw that out just to check it out. So over here, this is going to say the same. But when you rotate this, the methyl is going to come out, and your hydrogen is going to go in. Now, does it have a mirror plane of symmetry, or does it not have a mirror plane of symmetry? What do you think? You can cut this molecule right in the center. And this is a chiral center, and this is a chiral center, because they both have 4 different things on them. But it has an internal mirror plane. That's the very definition of a meso. You could have rotated this or this because they're both the same. So A is the same as B, and they are both meso. So when you take a trans and do an anti-addition, you would get a meso compound, provided that these R groups are the same. All right, let's try the same thing with a cis alkene. So cis alkene has got both the R groups on the same side. The mechanism's the same. You have a bromonium ion coming in and attacking from the top like this. And you form a 3-membered ring intermediate. So the bromonium ion here has the stereochemistry maintained just because we didn't have any kind of rotation or any carbocation that broke up the stereochemistry. The big bromonium mama ion sat right in the middle of the sofa there. Then your bromide ion then tries to relieve that positive charge by attacking it. Again, cannot attack from the top because there's too many electrons there. Attacks from the bottom. Equal opportunity to attack here or here. So it is non-stereoselective, 1-to-1. There's no preference of attacking one side over the other. So it's non-stereoselective. However, it is stereospecific. It cannot attack from the top. It can only attack from the bottom. The direction is fixed. So you get an anti-attack, anti-stereospecific attack. You don't get syn, you only get anti. So stereospecificity is anti, it's not stereoselective, and it is non-regioselective. It could have attacked here or here. Right? And you can see that the stereochemistry is preserved. What is on both the methyl groups are on the same side and both the hydrogens are on the same side. So stereochemistry is preserved throughout the reaction. Let's draw these out and see what is the relationship of the products. So here we have a pi bond. The pi bond is again your nucleophile. It's got a loosely held pair of electrons that can pop out and catch that bromine. Now your bromine, again, as we said before, is polarizable, and so your electrons can be shifting along that sigma bond, sometimes over here, sometimes over there, and so this can be at some point a more positive bromine, and this could be a more negative bromine. Your pi bond catches the positive, which is going to be your electrophile, and pushes over that electron to the Br minus. So now over here, you also would have a positive charge if you pull this out, but you don't form a carbocation because those electrons go sit right on top of those alkene atoms. So this big bromine mama atom sits right on top of that alkene, both sides covered on that sofa. So it's covered that entire alkene surface. So now you have a carbon-carbon bond, and the methyls are on the same side because at no time during this mechanism did we break that pi bond totally. It's always been there a teeny bit. This is your transition state. And you can put the positive outside, or you can put it here. Then when the bonds have all gelled together, you are going to get your bonds to the bromine as solid lines here. Now this is a positive, and again you can put it out here. The stereochemistry is preserved. We had both methyls on the same side, and they are going to be on the same side. We never got to rotate that bond. That's your intermediate. Now you can take this and attack again, just like here on this carbon or this carbon. Let's label them A and B. And I am going to redraw A and B here, and we'll do the attack from the bottom. All right. So I have drawn the intermediate here, exact same intermediate, no changes at all. I've just copied these over. And I'm going to now attack that, open it up with a Br minus. Br minus can attack A and pour in here and flip those bonds onto the bromine. That's one possibility. Let's draw that out. So here is a methyl and a hydrogen exactly in the same form. And now you could rotate them because they are sigma bonds, but let's follow our arrows and just draw it the way it is. There you go. So here is A because we attacked on A. And let's attack on B, and let's see what happens when we attack at the B carbon. So same thing as before. Let's say we have a Br minus coming in. And attacking this carbon here and flipping that over to those electrons over to the bromonium ion. So it can become neutral. And we'll have, again, let's keep it the way it is for right now, just to compare and see what relationship these molecules have. This is a good time for you to hit the pause button and think about it yourself. What is the relationship between A and B? Are they the same? Are they enantiomers? Or are they diastereomers? What's the relationship between these two? Let's look at it. If you put a mirror right here, you are going to get this molecule reflected just as it is. Well, that happened here too. Are they superimposable or non-superimposable? That's the second question to answer. Well, the only way to do that is to check it out. Take this and flip it 180 degrees. You're allowed to do that. And let's say if it is the same or if it is different compared to this. So this is the same molecule. This is also B. I'm just flipping it 180, making this go here and this go here. So when you do that, the methyl goes 180 to the back, and the hydrogen goes 180 to the front. And this so this is your B carbon here. Now that is going to be on this side. This carbon also does the same thing. Your methyl is going to go in, and your hydrogen is going to come out. Your bromines, well, on the B carbon is the bromine is going to be down, and on this carbon is going to be up, because we, again, as I said, we just turned that around 180 degree flip. Now let's compare A and B. What are they? Are they superimposable? We can take this, and if you put this on top, the methyl and the hydrogen are not going to fall exactly on top of that. Same here. If you take this and put it on top here, hydrogen is going down inside, methyl is going inside. Methyl's coming out, hydrogen's coming out. So therefore, these are not going to be going perfectly on top of each other, of the same atom on the other carbon. They're going to be non-superimposable. Yes, they're mirror images, but they're non-superimposable mirror images, and we only had one name for them. That's right, they are going to be enantiomers. A and B are non-superimposable mirror images. And that is the very definition of what an enantiomer is. Just a little summary here about the specificities. Stereospecificity is when you have a tendency to form a bond in a certain direction as opposed to any other direction. In this case, you're forming bonds that are on opposite sides to a pre-existing pi bond. As you can see, when you have cis alkenes, when you have anti-addition, it's anti-stereospecific because of the mechanism, because of the size of the bromine and the way it can only come in from the bottom. You can only have anti. There is no possibility for syn. So these are anti-additions, anti-stereospecific. But there is a 1-to-1 chance or probability of attacking either A or B. Therefore, they are non-stereoselective. If you'll get 50% of A and 50% of B. So that is going to be a raceme. For the trans, as we said before, because of the same type of mechanism, because of the size of the bromine being so big, it's sitting on both the carbons, and the other bromine can only come in from the opposite side. It is anti-stereospecific, non-stereoselective. A and B have the same opportunity to be hit by that bromine, and here you're getting two identical molecules from both attacks, and that is a meso compound. All right, so let's look at more additions to alkene. Now, I have shown this with bromine. You can do the exact same thing with chlorine. Okay, so wherever there is a bromine, you can replace that with a chlorine, and you can get these dichloro compounds. So bromine and chlorine mechanism is identical. Iodines, well, when they add, they tend to fall apart and come back to the starting material. So this is not a reaction that's done with iodines with this mechanism. Fluorines don't really work too well, with this. So it's non-stereoselective, but it's anti-stereospecific, and it's non-regioselective. So all of these give you a very valuable pool of stereochemistry-rich compounds in reactions, and that's something that we're looking for when we try to make compounds that have a certain stereochemistry for medicinal purposes or for any other purposes. All right, I'll see you guys soon, and just want to leave you with this thought. When you have a non-polar environment, there is equal opportunity to attack here or here. And so therefore, it is going to be non-stereoselective. We will come back and do the same type of reactions in a polar environment and see what the difference is. All right, sit tight, guys. I'll be back in a minute. Talk to you soon. Bye.